So last time we ended on this question of what really constitutes a minimal specification of a quantum state. And to answer that question, we devised the following thought experiment. Now the logic behind this experiment is the idea that if we want to know how to specify a quantum state, we need to consider the probability distributions of all of the relevant observables. Since we are talking about point particles without internal structure, those key probability distributions then are just the distribution of the positions of the particle and the distributions of the possible outcome of the momenta. Also, because at least for now we're really focusing just on one dimension, we will be just looking at positions of x as a single variable and also just the momentum in that corresponding direction. Now, the basic questions revolve around then what is necessary in order to be able to specify both simultaneously the position distribution and the momentum distribution. We are wondering whether or not, for instance, if we know the position distribution, whether that might be sufficient to actually know the momentum distribution. If that were the case, then we would only have to spy this particular distribution. And we do suspect there are some, at least, mathematical relationships between the two distributions, namely through the Heisenberg uncertainty principle. And the real question, though, is whether or not we can actually determine one from the other. So to get at that, we have the following experiment, which allows us to make actual direct measurements of a probability distribution along the x-axis and also of a momentum distribution as we cross over that x-axis. And the experiment goes as follows. We have a central line of symmetry, the horizontal line. We then draw our x-axis as a vertical axis, and right before the x-axis, right to the left, we put this blocking filter. Now the way the experiment operates is I have a source that's very far away from the origin. And so all the particles traveling from the source to the origin, I know, have traveled along a direction which is almost always exactly the value of theta naught. Now, as these particles then come through, they encounter my blocking filter, which has a transparency function which is near 0 at the edges and goes to 1 at the center. So particles really only get through this blocking filter, somewhat like in a single slit experiment, in a distance near the origin, and we've defined that distance to be this value sigma here. It might be better written as a sigma there, right? So then, in order then to determine, I'm inquiring as to the quantum state of these particles right as they get out of my source and right after they pass through my filter, where they then lay along the x-axis and have a certain distribution along x and a certain momentum distribution along x. In order to determine that momentum distribution, I have a photoplate, a straight photoplate that I can insert into my experiment. We call that photoplate 1, and very clearly that records the brightness across that photoplate. So I would say brightness from photoplate 1 as a function of x then gives me the probability, because the brightness after all just counts up for me how many electrons or photons land at any particular location. For the second photoplate that I could use, I use this semicircular. This was that first photoplate. For the second photoplate, I use this semicircular shaped plate. And the idea behind this photoplate number 2 is when I do a measurement, right, what it gives me really is the brightness along plate 2 as a function of angle. And this then constitutes a momentum measurement, because if I look at a given angle, if a particle lands at that particular angle, say at angle theta, the location where it landed is determined not so much by where it happens to get through the filter, because this radius has been chosen to be super large compared to the region through which the particles can actually pass, but rather is determined primarily by the direction of motion of the particle. And that direction of motion of the particle is determined by its overall momentum magnitude, which we know directly because our source had a pure energy E from which we can know at least the magnitude of the momentum. And then by knowing the angle theta, that constitutes then a direct measurement of the x component of the momentum. So That then, this second brightness that we can measure across the second photoplate then tells us the momenta of each of those electrons, and from that then we can infer then their corresponding momentum distribution. Now, before we begin considering the outcomes of this experiment and the lessons which it teaches us about the specification of quantum states, there's one last technical detail that I want to fill in for you, which is this transparency function. I'm going to sketch it for you here. The actual function we're going to use, we're going to pick actually a particular function. It will be a function of x, and we really can think of this it's often called a transmission function. A transmission function is a function between 0 and 1, and it tells you what fraction of the incident brightness actually gets across the filter. And so in the center here, I'm going to allow all of my particles, if they hit at exactly x equals 0, to pass through. So the transmission function will start at 1, and then it's going to have I'm going to use a nice Gaussian shape with an actual Gaussian function that has a true standard deviation of sigma, and such a function can be written in the following way: e to the minus x squared. That makes a Gaussian, and if I want it to have standard deviation sigma, I divide in the exponent the x squared by the quantity 2 sigma squared. And you will notice I've chosen the normalization on this so that indeed when x equals 0, my transmission factor actually hits 1. So our job now then is to use all that we know from our de Broglie hypothesis in order to predict exactly what these probability distributions are through these brightnesses that we can expect to arrive on these two photographic plates. We know we can predict those brightnesses using standard wave physics because we know either light or electrons produce exactly the same types of diffraction patterns as we know through the G.P. Thomson experiment.